It's my honor to introduce the annual Historical Colloquium, which comes around at a random date, but once a year. So this one today is particularly special because our speaker has flown over from Beijing specifically to give this lecture. We knew that this was going to be a good lecture because we heard the story of the IAU meeting in Beijing when he gave a lecture to a full house, and there were so many people who hadn't had a chance to hear it that it was rescheduled, and he gave it again a few days later to another large audience. So Professor Sun is a member of the Chinese Academy of Sciences Institute for the History of Natural Sciences. He has, amazingly, a pair of PhDs that he brings here. One he got at the University of Pennsylvania, working on aspects of natural sciences in the Sung Dynasty, which I'm sure you'll all know was between the 10th and 11th, 12th centuries, working on alchemy, astronomy, and medicine. And a second PhD from the Academy of Sciences in Beijing, where he worked on Chinese constellations in the Han Dynasty, about 100 BC. And that was published in 1997 by Brill Publishers in Holland. So I am very happy to welcome Xiaochun Sun here for a colloquium, which, as you can see, is on sky gazing and season granting, astronomy in ancient China. Please.
Thank you. Thank you, Professor Gingrich, for this kind introduction, and I'm greatly honored to be here to talk on this topic. You see, about more than, I think, 25 years ago, when I was a graduate student, I was reading Irving Gingrich's articles already. So today I feel especially great, to have you introducing me and to have this opportunity to talk to you. And also, of course, I'm thankful for Dr. Zhao Ping for when we introducing this, when we met in 2012 in Beijing, and we had a good talk, and he suggested that maybe I should have come here to give a talk. And also, especially, I have one of my colleagues in Nanjing University, Dr. Zhang Shizhou, is also here, so I'm really excited. So today my topic is about astronomy in ancient China. Yeah, astronomy is perhaps the most advanced science in ancient China, and perhaps the one that shed most light on the Chinese civilization is astronomy. I think in order to understand what the scope and the meaning of the Chinese astronomy, two concepts I think are essential. Yeah. So one is the Chinese consider there was a strong relation or interaction between the heaven and the man. So everything man do should follow the cosmological rhythms. For example, we have this kind of monthly ordinances, and also in doing this, of course, the calendar making was very essential. So that's the first concept, the interaction, the correspondence between man, what is above, and man and heaven. Yeah. The second concept I think should be the concept of change. Okay, I see Tianson here. Very nice. Okay, yeah. So change. That means in the philosophy of Chinese, it's everything changes, and also there is no distinction between the celestial and the terrestrial realms. So everything in the sky is composed of the same substances as that on the earth. So what is in the sky is not eternal, not incorruptible, not perfect as the Aristotelian cosmological view would have seen it. So this is very essential for the Chinese, for understanding the Chinese astronomy. There was a book actually called the Book of Change, which says that heaven hands up its signs, symbols, from which I sing good and bad fortune, and the sage makes his interpretations accordingly. So that's the two things, concepts which I think I should first introduce to you. And of course, this perhaps we can find a clue in why the Chinese think this correlation is so important. Actually, there was one creation story about the universe. The universe actually was created by a man, human body. So this giant person called Pangu, when he dies, when he exploded, so his bones, becomes rocks, his flesh, blood becomes rivers, and the sea, and his hairs become stars. So in the universe, composed of such human substances, it's understandable that there should be such strong correlations between the universe and the man. Now, it's, of course, in such a short talk, I cannot really give you a complete story about the Chinese astronomy. So I would like to choose some topics, some of which I have been studying recently, to just give you a glimpse, highlight some important aspects of ancient Chinese astronomy. I will choose 5 of them, and I didn't list here, but the first is about most ancient times. It's about the beginning of astronomy. So this is a prehistoric Taosi Observatory. I just want to give you some very brief introduction of the early history of Chinese civilization. We have these 3 dynasties. This is Xia, Shang, Zhou dynasties. This we usually know, and particularly during the Song dynasty around 1200 BC, there we know we discovered these oracle descriptions, the Chinese languages. Before all these 3 dynasties, there was legendary sage kings like Emperor Yao and Shun. And this Taosi site, this Taosi culture, which I'm going to talk, is around 2300 and 1900 BC. This is about the discovery of the Taosi site. So it's here, and here is the Lingfen of the Shanxi province. The Taosi site is location is this. Okay, so we know this place historically. We know is connected to this emperor or king Yao, because even the place names of such, for example, the city, there was a district called the capital of the Yao's kingdom. Okay, so in 2003 and 4, Professor Honu from the Institute of Archaeology of Social Sciences, Chinese Academy of Social Sciences, discovered a semicircular structure attached to the southeast wall of the city. The city is about 2 square kilometers in area. So perhaps the largest in the prehistoric China, indicating the emergence of the pre-dynastic kingdom. Here, and in this site, we discovered very important items. For example, this is a bronze. This is like a cogwheel. Okay, it has 29 teeth. So it's very interesting. Why 29? Yeah, and anything related to the lunar months? Yeah, we don't. And also we found discovered the maybe one of the earliest Chinese characters. Yeah, this is which painted on the pottery, and this is the foundation of the Taosi altar. And this is the escape of the Taosi site. You see it's a semicircular structure with pillars aligned in a way with intervals in it. So from the center point, if you look outside, these slots will serve as the backside for observing the rising sun. Okay, So here is the scheme. You see, there was 12 slots, but this southmost one is beyond the amplitude, the range of the sunrise. This is for the winter solstice, and this for the summer solstice. Between that, here there's the spring equinoxes. So this structure is very, but the question is, why do you think they should observe here? Yeah, are there anything indicating that was the observation spot? So they did the excavation. Actually, they find that near the place they calculated there was a circular area which rammed the Earth. It looks like a small platform. So that's probably the place served as the observation spot for the observation of the rising sun. These are the people, we did the field trip to that location, and this is me, and these are the group of historians of astronomy in China in 2005. We erased some frames to do simulative observations of the sunrise. And this is our working with, based on the base of the wall. We erected this brick structure and just as a working model of the structure. Everything is underneath. Yeah, we didn't destroy the structure. And this is a sun. Actually, you do not have to really look at the sun to go to. When the sun rises, it just casts its light. Very, very, very obvious to that center point. Now this is about it's possibly was the structure used for observing sunrise. So in order to determine the seasons, determine the time. So it can be served as a kind of a horizontal calendar. Yeah. But that's, of course, is a hypothesis. Yeah. But we are fortunate that during our research, we are also told that the archaeologists in those tombs discovered a painted stick, which they didn't know what's the use of it. So we suggested that it could be probably used as a template for the glow moon. So we made some simulative observations, in the field, and okay, this is for the horizontal calculation we did. I think I just skip here how to determine the date of this structure. So we assuming that the method is like this. For each year we have 20 sunrises seen through 11 slots on the 20 days of the solar year. Treat them as 20 observations. For each observation, compute the deviation of the center of the sun from the center of the slot. Calculate the standard deviation for the year. The year with the smallest standard deviation to be the date of the structure. That's our assumption. Of course, this cannot be really, we cannot, that's the, these circles are the sun view from in the slots. It's not so decisive, this way. We may find some, the deviation getting smaller, but it's not so decisive. So the real date must be, the dating must be, assisted by the archaeological method. Yeah. So these are Julian dates for the sunrises in the slots. Also, there's one, this southernmost, this slot, what's the use of it? It's about 5 degrees even south. So we immediately, of course, it suggests that maybe it was used for the observation of the moon. Yeah, when the moon comes to one of the major standstills, yeah, it appears in that, rises in that slot. So the function of the slot even maybe, it shows this kind of circle, yeah, 1868 circle. Now about this glow moon. So this is original, which with Earth, the block Earth contained this painted stick, and this is a reconstruction of the painted stick. It is painted 3 colors with 3 colors. This red, green, black. You see, it looks like these red ones. other marks, for measuring something. Yeah, okay. So we thought maybe this is for the winter solstice. For the summer solstice, the shadow of the glomo. So that's our this is the tomb where the painted stick was discovered, and we doing simulative observations. So the use of the template. So there is a 8 chi, it's about 2 meters high glomo. With its shadow, the lens at the summer solstice comes to here. And then if the stick is 1 meter and 78 centimeters. It's not long enough for the shadow of the winter solstice. So it's flipped over, then it's come to here. This is the length of the shadow at the winter solstice. And we also, it's interesting that according the excavator, they say when they discovered the stick, some part of, because it's erected in the tomb, some part was cut off, because in the beginning they didn't know there was something there. So, and in this way we can even determine how much was cut off. Yeah, so because we know the length of the summer solstice shadow and the length of the winter solstice shadow. So that's we can comparing the dates derived from sunrise observations with those from the glomo measurement. Yeah, so that's this is perhaps much more. Yeah, these are the strips on the glomo, and these blue lines are the dates determined by the slots on the horizontal structure on the. Now this is about so that's probably we can serve as a kind of a evidence that at that time this place must be an observatory. Also important, we can probably compare this to Stonehenge in Britain. But Stonehenge, you do not have any record, historical record about. China, it's interesting to see. There's one book called the Book of Document. There's a chapter called the Canon of Yao. Yao means the Emperor Yao, the King Yao, which I mentioned, one of the legendary. Of course, this book was compiled much later. It's about around 4th century, between 4th century to 2nd century BC. But in this book, there's a chapter. It says that the emperor commanded the Xi and the Hou, these two astronomers, reverently to follow the august heaven, to calculating the delineating the sun, moon, and other celestial bodies in order to respectfully grant the season to the people, and to take 366 days by using intercalary months to fix the seasons. So this is a Qing. It's a 18th century representation of the legend of the story about the Xi and Hou brothers receiving commissions from the Emperor Yao to observe the stars. Now, in this book, also 4 stars are mentioned. These are the 4 cardinal asterisks. That's indicating the winter solstice, summer solstice, and the 2 equinoxes. They say the day of the medial length and the star is bold. Okay. And the middle spring is determined. So you have these 4 stars. Formerly, there are some studies of these 4 stars. For example, these are earlier datings of the 4 cardinal asterisks. And Gaubier, the French scholar, he determined that these observations should be made between 2150 and 2796 BC. And Zhu Kouzhen, he said all these 4 stars has different dates. So now when I did my dissertation in Amsterdam also sometime, and we assumed that these 4 stars should be treated in group as a system, not separately. They should probably indicating the 4 cardinal points in the sky. So the way to date, we just placed in a way so that at a certain date it fixed the 4 cardinal points the better. So I So we did this, and we placed the date around 2400 BC. So that's many years before the discovery of this Taosi site. So now for this site, now we have this horizontal structure, this and also this chromo, and also we have literature references. Although it's not from that time, but it refers something very old, this old tradition. So this way probably can help us to come to a conclusion that by this time, by the 21st century BC, astronomy reached a considerable level in China. 3 basic techniques for observations were already used. That is observing the rising sun, and the second is chromo observation, and the combination of the stars. So that's the three most fundamental ways of ancient Chinese astronomical observation. And this Taosi site had functions of astronomical observatory, the observation of the sunrise, and probably also of the moon. Okay, and this Taosi site also related to this Emperor Yao, this King Yao. Yeah, so for this early history, formerly we do not know much about these early kings, but nowadays, as archaeology has discovered more and more sites, it's become the early history, early civilization of China become we have much more knowledge about this than before. Okay, so this is about the early stage of the Chinese astronomy. The second topic I'm going to talk is about your instruments. Of course, doing astronomy is science of observation, and in observations, instruments is very important. I will particularly to introduce you about the reconstruction of Suzhong's water-powered astronomical clock tower. This is from the 11th century, as Owen just mentioned, it's of the Northern Song dynasty. You see, this is a chromo of Beijing Ancient Observatory. In order to raise the accuracy of the measurement of the length of the shadow, the 13th century astronomer Guo Shoujing, he just enlarged the chromo 5 times. So in this way, he can improve the accuracy of the global shadow measurement. And this is essential for the determination of the time of the winter solstice, which all Chinese calendrical systems, astronomers calculate, the starting point is the winter solstice, not like nowadays we're probably using spring equinox, but in China it's winter solstice. And these are the armorial sphere, which is from this date, now in Nanjing Purple Mountain Observatory, and this is based on the Guo Shoujing's earliest design. The philosophy behind this kind of instrument is that when you realize there is a circle in the sky, then you just add one to it. So there's the ecliptic, then you add an ecliptic circle to it. You're horizontal, then there's a moon's path, then you add another ring to these concentric circles. In this way, by putting the sighting tube to any object in the sky, you can read the data from the rings. So this instrument is not only just for observation; it's a kind of a cosmology. It's a projection of it's a microcosmos in a way. So, but this is nice. But when it comes more and more circles, it becomes a problem because it block the many areas, particularly the areas along the ecliptic. Yeah, those places you want to observe, but it was blocked by these rings. So by the 13th century, this Guo Shoujing tried to solve this problem. So he made this instrument that we call a simplified armorial sphere. He just remove those, first the meridian, and place this equator, put it to the bottom of the axis, the one lower end of the axis. In this way, it has the whole space, which you want to observe, nothing to block it. So that's equatorial mounting, like nowadays we do, you know, with the telescope. Yeah, so that's very, very clever. Now, to make observation, you have to also to follow the star, like you have to use a clock to track the stars. And of course, the Chinese, at lunchtime I mentioned about this water clock, the way to, you know, to keeping time. This is a water clock from the Han Dynasty. Okay. It's just one vessel, so you have the water. You feel the water, and the water pour out from this leak, from this hole, and then as it drops, water level drops, the indicator. There is an arrow indicator will fall. So in this way, this can tell the time. But then the question, of course, when the water level fall below, the speed of the flow of the water becomes slower. So that means the time is not even, you know. So so at the Song time, at the 10th century, there was people thought of these ways to, you know, first they have several vessels. So in these middle vessels, when this water level was kept constant. So if it's full, it's just overflow to this drainage. Okay. So in this way, they can keep this. Also, siphons were used. You know, water temperature also were controlled. Sometimes they even use mercury, using the mercury instead of water, so to maintain the speed of the water. So that's so similar things you can also see in Greek word. This is in Athens. You can find this water. Maybe it's inside nothing, but we can imagine it's something very similar to what we are going to see now about Shuzong's clock. Now Shuzong, he was official from the Song, northern Song dynasty, and his highest position was the prime minister, actually, when he constructed the astronomical clock tower. This clock tower was water powered. That means using water from the water clock. So in this way, and then it has a central wheel, and this central wheel was powered by water, and will drive this armillary sphere. That's for the measurement of the coordinates, and drive the celestial globe. That's on stars or placed on this globe, painted on this globe, so that you can demonstrate the movement of the sky, and also to drive this jack, you know, timekeeping jackpots, the jack wheels. It has several wheels to indicate the times in various forms, and at a certain. It has figurines, you know, and also drums and gongs, you know, to announce the time. So it's an automatic clock. So the whole thing is all automatic. But then how to make the water powered the wheel to move to, you know, in a clock way, you know, it's not the continuous way, but have to like this control the movement. So the thing about it is something similar to escapement mechanism. So that's what Shuzong achieved when they made this instrument. This original instrument is about 12 meters high. So it's very large, 7 meters across. So it's an automatic observatory. Now, for past 3-4 years now, we try to make a study of this water clock, and formally about this mechanism, escapement mechanism. It was believed in these central wheels. You know, this central wheel has 36 scoops. When the scoops was filled with water, it will flip, and then it trigger off pull down a bar which locked the wheel. So that's the way of the escapement. I will show you. But this was based on a study by Cambridge. This is we call the flip scoop model of the escapement mechanism. which hypothesizes that the 36 scoops attached to the central wheel were not fixed but can flip as it was filled with water to trigger off the celestial balance. Okay, I will show you. Here is the celestial balance. So when the water here, the wheel is missing in the original. He couldn't produce it, but when it is a scoop is filled with water, it pulled down this line, and the celestial balance was lifted so that the wheel can move one step. So that's the escapement mechanism. But we think, according to the original, the text is by Shu Song. He wrote a book called 新一项法要. That's the essentials of the new instrument. There are some aspects which is there's this slope, this soft rope, which in Cambridge's model it was not used. There are also here something like it is called a rabbit's head with two ears. And in Cambridge model, it says it was just for decoration. Okay, and also mentioned that there was a crane, like the leg of the crane, moved this way. This was also not necessary for Cambridge's model. So we think, since in the original text says the scoops, 36 scoops, were all fixed, why we don't try a fixed scoop model? So we did this experiment and reconstruction based on this model. So this is the flip model of the escapement, which is based on Cambridge and Nature 1964. Yeah, and this is our fixed model of the escapement. It's not really escapement, but yeah, it's different from mechanical clock. But Joseph Needham called it escapement. Yeah, I think it was wrong. Yeah, it's not. Yeah. But that's the Chinese way, to control this kind of a movement. It's a mechanism for control the movement. Here is our model, and so on this is the so-called rabbit's head. As it actually plays its a role in the whole mechanism for the controlling of this movement. So I just show you this side are the pictures in the book which are made by Shu Song, and these are our reconstruction. And this is the water clock, and here we also do it. The armoured sphere, and the supporting it, these dragons, it's so beautiful. And that's what we did. The celestial globe and the time reporting jack wheels. Now, so I think this model now is on exhibition at the National Observatory, Astronomical Observatory in Beijing. It was exhibited during IAU 2012 in Beijing. So now it's possible that in Shanghai we're going to build a one-to-one scale, the original size reconstruction. So our fixed scoop model is not only the mechanically sound, but fits the original description by Shu Song better than the flip scoop model. Actually, this is I'm not going to go deeper into it. This is a Chinese mechanical realization of the Chinese conception of heaven and man in one. So everything you should follow that. So that's a mechanical realization. And also for observations, it's get rid of the human errors. That's what Shu Song also mentioned in his book. Because you say when there are people, argue about whether whose observations are more accurate, then there was a big controversy at his time, and this is a way to solve this problem. Now, the third topic, I still have time, about another aspect. Formerly before is about observation, but now it's about this season granting. It's about timing, calendar making, the computation of the planetary motions. Yeah, the Chinese calendar actually is not just a calendar. It's not arranged. it's an astronomical system. It's an assembly of mathematical techniques for producing ephemeris and for producing almanacs, even for producing, so method for the prediction of the celestial phenomena, and of course solar eclipses, lunar eclipses, and also the movement of the planets, like conjunctions, retrograde motions, standstills. Now, the Chinese, so what is calendar? It's you find all kind of circles, basically, day, month, year, and then you have the synodical months of planets. So you just eventually find a large circle, the largest epoch circle to include, to contain all smaller circles. So that's the philosophy behind the Chinese calendar making. Just for example, if you consider this is 1 month, 1 year, this is 19 years. So 1 month later, the month will go complete 1 circle, but the others not. And then this is 1 year later, and then the end of the large circle. So that's for the 19-year circle. So that's the Chinese circle for placing intercalary months. So 7 months, lunar months added to in order to make the solar and the lunar calendars to keep in step with each other. So, but the Chinese, of course, this is a philosophy behind it. But then the Chinese calendar was very ambitious. It want to include everything, not only celestial movement, even dynastical change. So it's not just about the sky, but also our human society. So that could produce a system with such a large circle, such a period. It could be millions of years. So in that way, this calendar will become perfect. So that's the philosophy. Now, of course, the planetary motions computation is essential. So this is the first existing calendar from this date. The synodical period of the 5 planets is derived from this calendar. For Jupiter, this is a modern values. Of course, then the question is how the Chinese calculated this planetary movement. It's very different from the Greek ones. You all know the Greek ones. There's epicycles different and equal, all these tools. But the Chinese use a numerical method. So that they divide the sausages into several sections, stages. For each stage, they have a certain speed. So in that way, they produce that kind of a piecemeal function for the speed, apparent speed of the planet. So in this way, it approaches the actual curve, the curve of the actual movement. So mathematically, it's different. One is a geometrical, but the Chinese are numerological. But the effect are similar. So the numerical way can also attain a very accurate level in terms of the prediction of the position of the moon. So this is in the calendar of the Taichu from the 100 BC. It is the 1, 2, 3, 4, 5, 6 stages, and which each stage is apparent speed, and the station, of course, speed is 0, and how many days they maintain such a speed. In this way, they can produce. So I will show you. It's like this. These green lines are based on the calendar, and these blue lines are the actual movement. Okay, so you see, it's not perfect, but it's it's approximation to the actual movement. So that's from 100 BC. Then later on, how to improve it? First, they divide the movement into more segments, into more sections, and in each section has their own speed. So you see, in each section, more sections, and later on, after the 6th century, when the unevenness of the planetary motion was discovered, they also introduced it into calendar. So each stage, the speed is not horizontal, it's not a constant anymore. So you can see This is one of the calendars from 700 to 8. You see, this speed line looks like this. You see, much closer to the actual. So you see the, and this another one from the Song Dynasty, from the early 12th century. You see, this is much better. Now I come to this is exactly the same. I just mentioned this Zhang Zixing. Zhang Zixing, he from the fifth this time, he observed 30 years and spent 30 years make observation, and then discovered this unevenness in the solar movement, sun's movement, and the planetary movement. And less than 100 years, you know, these discoveries was incorporated into calendar making. So you can see this kind of curve was used in the prediction of the. And of course, I just show you how this is the record of the planetary phenomena, the entries on planetary events in official histories. You can see around this time, 500, there was a peak here. So that means people at that time are more concerned about this planetary motion. So that's why you have see. Of course, these are for these events like conjunctions, retrograde, and it's come closer to certain constellations, etc., etc. So these are for astrological purposes. But you can see people are concerned about this, and you can see also Chinese, you know, in the history produced some more than 100 calendars, and you see around this time, the average error in synodical periods derived from calendar in the ancient China, you know, suddenly become quite, you know, formally it's so big, the error, but from here it's become quite accurate. So you see the trend. Now, I want to show you one interesting thing is that there's about the Mars. Mars is difficult to study, and Kepler, of course, waged his martial war, you know, and in this he discovered, you know, the 3 laws of our planetary motions. And the Chinese, this Mars also have a very interesting name. It's called Yinhuo. Yinhuo means it's really something hard to track. And now these are the above is a study made by Professor Gingrich, and he showed that in I think it's a Copernic-based data. These are protonic tables from this date. The deviation, you know, of the Mars has this pattern. Most of the time it's about 1 or 2 degrees, between 1 and 2 degrees. But sometimes in, you know, 32 years, it could reach some nearly 5 degrees. So that's a kind of a catastrophe. Yeah, it's a crisis. Also in China, from, you know, this Ji Yuanli from this date, according Tang, one of his study, you see the deviation has the same pattern. Oh, yeah, 1 or 2 degrees, but sometimes reached to this 5 degrees. So you can see in 11th century, the Chinese, this numerical method, already in terms of prediction of the Mars positions, reached the same level in the 16th century, just before Kepler, of course. Kepler laid on much precise, more precise. So now I ask a very interesting question: why didn't the northern Song China produce a Kepler? Yeah, so they have the same problem. They also have astronomers to do this. Not, of course, not in terms of the models, geometrical number, but they should have this problem. They should have a way to solve it. So the Kepler, I just skip it. Yeah, and at that time there was one person called Shen Kuo. He is also a polymath and also a very high official. He actually noticed this problem of in the calculation, prediction of the planetary motions. And here is a crisis with the Mars. The emperor himself in this year, the emperor said, well, I was consulting the almanac based on this system, a calendar. It says Mars will retrograde up to the numerology chariot, then in the modern constellation Corvus, before it proceeded eastward in direct motion. But now it had retrograded only to the numerology home. in Virgo before it resumed the direct motion. Is something wrong with the system? So even the emperor realized there's a big difference, big error in the prediction. Of course, then the officials have to respond to this. Some, of course, respond with flattened ignorance. Yes, well, this is the heaven above helping the virtuous ruler with a good portent, not something that mathematical astronomy can predict it. So, and some take this opportunity, well, we should test these various calendrical systems. So this Zheng Zhaoyan, he saw the planet in the planetary event a good opportunity to improve the astronomical systems. And they tested the 3 calendars. These 2 are from the previous dynasty. It looks, but the final result is the previous dynasty calendar, this one by a monk, Yixing, is the best one. Yeah, so it's a shame, you know, for we can even not produce a system more better than the one previous. So the serious response was made by this Senkor, this polymath. He said his program is to predict the apparent positions of the planets, not merely the mean speed and prominent phenomena. And a new computational method he called 赘数. The computational tools available did not permit this to be done with few observations of stationary points, occultations, and maximum elongations. So he suggested to plan a series of observations of a kind not proposed in Europe until the time of Tycho Brahe, 5 centuries later. The exact coordinates read 3 times a night for 5 years. So he said, excluding those rainy and cloudy, the moonlight days, we can at least have 3 years of data, and then use this stitching method. 赘数 means like stitching method. We can have a much better prediction of the planetary motion. So, but Senkor, he proposed to improve the planetary theory, but his project failed. So he made a new instrument, but simply at the astronomical bureau, the observatory in Piri, people just would not work with him. Yeah, okay, no. So I think he complained about this, but I want to show you what's the reason behind it. First, technically, the criterion used for testing the accuracy of the planetary theory was problematic, which emphasized the number of fitting cases between calculation and observation, while avoiding predictions at a crucial moment. So the real system, whether good or not, you have to see those crucial moments, not the average. If average, it looks real, it's not too bad, because average looks around 1 or 2 degrees. Yeah, so that's the way the testing the calendar is not. Politically, the important astrology, planetary events did not present omens as conspicuous as solar and lunar eclipses. An error in the prediction of planetary events would not raise alarm, as failure in solar prediction did. So even emperor sometimes notice this, but if something wrong with the eclipses, that will become very serious. Yeah, some even say the astronomer could be executed. Yeah, so that's, but not in case of this planetary motion. So there was not much political motivation for improving the planetary theory. Bureaucratically, incumbents in the astronomical bureau were actually very unwilling to bring change to their routine work. When Senkor proposed to improve the planetary theory, he needed a continuous observation of the planets for at least 3 years. He did not get support on this from his colleagues. On the contrary, he was interrupted with fierce quarrels between talented astronomers and incompetent placeholders. So that's the situation in the Imperial Astronomical Bureau. And politically, okay, I think I should have went. And personally, also interesting, Senkor, he has a relationship with Wang Anshi, one of the great reformers in the 11th century. Actually, he produced the banking, proposed a kind of a banking system, very only later on the capitalist way, reform. And this Wang Shi appointed Shen Kuo to the astronomical bureau, and this is a critical position because astronomers, astrologers, sometimes they're using astronomical abnormal events to criticize the policy, to criticize even the emperor. So when Wang has these new policy reforms, of course he made a lot of his enemies angry. So these enemies used this. As one of the enemies is Sima Guang. He's ardent, and he appointed Shen Kuo to replace this Sima Guang. He is ardent opponent to Wang's new policy reforms. But somehow Shen Kuo didn't do the job very well. So Wang Shi was not happy with Shen Kuo's performance. Yeah. So okay. So I just show you how I just read what Shen Kuo himself complained in his book called Jotings at the Dream Brook. And he said, formally, we do have a lot of corrections, reforms. But what we do is not really, we are not solving the critical problems. We're just adjusting these constant to make it to fit the current situation. But a few years later, it will, the small errors will accumulate, and again, the current is not good enough. So unfortunately, he said, most astronomers then inherited their positions from their fathers or grandfathers. They were just placeholders satisfied with receiving salaries, doing nothing. No one really knew the calendar. But they were jealous of Weipo, that's the person he introduced, Tarrant. They slandered Weipo to collectively even bring accusations against him at court. Though they could not do actual harm to Weipo in person, the proposed astronomical observation was out of the question. In the computation of planetary motions, Weipo had to make do with correcting some constant in the old systems. There was no match to Weipo's talent in calendar making, but his talent could not be used. What a pity. So that's what Shen Kuo said in his. So actually at that time, so you see all these factors, it's very bad, of course, but also there are some favorable situation. For example, economically, at that time, Song government spent a lot of money on astronomy, because astronomy gives, the good calendar legitimizes his rule. It's symbolic. So you see, this is the fiscal income of the Northern Song. So at this Shen Kuo's time, this current is something already this number. And this is the financial support for astronomy. So these are the monies invested in astronomy. This is the whole fiscal income, and how to achieve this data, we adding up the salaries of those positions and how much the instrument, etc. These are data, we have this data in the historical document. You see, for this period, almost nearly 0.1% of the total fiscal money revenue, was invested in astronomy. That's a very big number actually. Nowadays, for example, in 2007, the fiscal income of China is this much, and astronomy about this much. So counting only about 20 times less than in the Northern Song. This is also a way to see why China, in ancient China, astronomy was so developed. So that's probably why before, Copernicus, before Kepler, scientific revolution, astronomy in ancient China was so. On the planetary motions, China in the 11th century could have achieved more. Political and bureaucratic reasons made it hard to make real innovations. So, and when scientists were forced, in a way, they were forced to make innovations because there was a new emperor, they want a new calendar, they wanted it very immediately. What could they do? What they can do is just adjust those constant, not really solve the problems which Shen Kuo was in mind to do. So, like situations sometimes even now in China, when we are asked to produce papers and in Nature, in SCIs, and very quickly, what can we do? So, so that's a very similar situation. Now, here is for astrophysics. This fourth topic is about celestial events, the observation of celestial phenomena. China had the longest, record, continuous record of celestial phenomena. Of course, for the purpose of astrological, more or less astrological reason. But these actually provided data, some data could be useful for more than astrophysics study. And all kinds of phenomena, because you see, as you can see, the philosophy of change, they even anticipate changes in the sky. So they will keep always on the lookout what's happening on the sky. These are the solar and the lunar eclipses. The earliest one probably also recorded in the book which I mentioned, the book of document. It's interesting to see that on the first day of the third lunar month of the autumn, the sun and the moon was in disconcert with each other in the constellation house. The blind magicians were so alarmed as to beat the drums, and the local officials rushed and the common folks panicked. So that's the situation. And also in the oracle descriptions from the 13th, 20th century BC, which I mentioned earlier, and there are also, mentioning of the lunar eclipses and the solar eclipses. And this observation of the comets, these are from the Silk Book from the Han Dynasty. You see, this description of the tails, the picture is, we can see the observation is meticulous. It's very, careful about the details. And these are the Northern Lights, which is from one of the Ming Dynasty from 14th century books. So these are paintings. Now, of course, these this Kepler nebula. This I think all of you know. So, but I said another one also from the Northern Zone is from 1006, and these are the texts which are recording this what they see, and actually from these descriptions we can get the brightness, the magnitude of the star, of the supernova, we call supernova, for several days, for example. So you can kind of have a kind of estimated a light curve of this, and these we do the observation was actual. It's not because when you adjust the sky to that time, you can see for when he says it is as bright as the Venus. Actually, Venus was in the sky. So it was as bright as the half moon. Actually, the half moon was in the sky. So it's not imagination. That's because that's the only way you can compare the brightness of the two objects. So that's I just want to. Anyway, so finally we can produce a light curve like this. Perhaps your light curve type 1 supernova is so. Yeah, that's what. I think it could be. And also there are some other kinds of records, such as the sunspots, comets, meteors. It could also be used for analysis, for study of the solar physics, or even nowadays for environmental, the earth sciences. So these are the sunspot records to verify long-term solar dynamo matter. These are studied by somebody, I think Osokin. And celestial events and Earth environment. A signature of a cosmic ray increase in. There is one paper by a Japanese scholar in Nature, just recently, and there was a dramatic. Also in China, there's a Professor Sun Weidong from. He also a dramatic increase of radiocarbon in coral form of the South China Sea at the same time. So maybe this is the paper by this Japanese Fusa Miyake. And now could, of course, this increase of the carbon-14 elements in the Earth could usually be caused by supernova, or could it be, yes, this Professor Sun, he suggested it could be also, that's a suggestion, because during that year there was a record of the comets. This comet is quite from these around this date, 773, with a coma that stretched across the whole sky and disappeared within 1 day. What does it mean, the whole sky? So that means it should be entered into very close to the Earth. So that's a possible explanation. Okay, so that means in China we have these kind of records abundant. I estimated about 20,000 entries of all kinds of astronomical events. I think some of it already used, but I think this is a treasure that still can be used, for modern scientific research. Finally, I just want to talk a little bit about the Chinese constellations to see how the Chinese had a system which is very different from the Greek system, from our modern system. Okay, the 88 constellation. It was basically the Chinese society, the Chinese empire, projected into the sky. So it's set the background for making this correlation between heaven and the man. And you see, for the central Paris, for example, the polar area, the pole star is fixed. So there's the Confucius saying, if you are a ruler, you should rule like the pole star. You're just sitting there and all others turning around you. So this is the concept of a central government. So it's deeply rooted in the Chinese culture. Yeah. So even you see it in the sky. You see, and this is the Tianguan Shu by Sima Qian from the person who also participated in the calendar reform first about 100 BC. He said the brightest star of the celestial pole is the permanent abode of the great unity. The 3 stars next to it are the 3 lords. Although some identify with as princes, curving behind it are the 4 stars. The largest star in the rear is the empress. The other 3 belong to the imperial harem. The 12 stars that surrounded all of these, framing and defending them, are the vassals. All of these made up a purple palace. So this is the forbidden city in the sky. So it's very, and also the other part along the equator and the ecliptic, you see all the 3 stars are correlated to the human environment according to the seasons. For example, in the autumn sky, you see such constellation like Tianchang, celestial barn, celestial grain store, celestial granary, ricks of grain in the field, cesspools, reaping sickles, photos. It's agriculture, the farming scene in the sky. And this is a picture, to see to give you an idea. And a picture of a farmer's life in the sky. For example, here you have this we call a winnowing basket. There's a winnowing basket in the sky, and there's a chaff, and also there's chaff around. So you can almost everything you can imagine in the society you can find in the sky, even a toilet, for example, even a crap in the toilet. It was meant to construct the sky exactly as our human society. In this way, the correlation, the correspondence between heaven and man can be interpreted straightforwardly. So that's a reconstruction of the Chinese. So, for example, the northern dip, the great, is the chariot of the emperor. It controls the 4 quarters of the by moving around the center. It separates yin and yang, establishes the 4 seasons, distributed the 5 phases, regulated the celestial movement, and determining the celestial epochs. All these depended on those northern dip. So this northern is like a chariot moving around the center. That's a symbolic way, to represent the Chinese way of governing. These are the map from the Han Dynasty, from the Xi'an. I just, these are the, one of the earliest maps. These are now in British Library and the Dunhuang collection. This is the Forbidden City area. Yeah, this is the northern Dipper. Yeah. And this is the whole sky of the Chinese, the planisphere of the Chinese sky from the 13th century, now in Suzhou. Yeah, so on the stone. So I think I will stop here. So I just talked these 5 topics. I just want to give you a glimpse of what Chinese astronomy looked like. So maybe I just say a few remarks. Yeah, for a period of over 3,000 years, China made tremendous progress in astronomy. It maintained the longest continuous record of all kinds of astronomical phenomena, still used for today for astronomical research. It made more than 100 astronomical calendars, each being a sophisticated system of astronomical computation. It constructed a large number of astronomical instruments, culminating in the construction of the astronomical clock tower in the 11th century. Okay. And ancient Chinese astronomy, the most essential part of Chinese inquiry, is to inquire the connections between heaven and man. In doing this, the Chinese made a remarkable achievement even from today's perspective. The consciousness of man's position in the universe is still meaningful in modern astronomy. Yeah. Thank you very much.
Well, thank you very much for this long history and interesting survey of it. I have sometimes contemplated writing a book entitled Aristotle's Error. And Aristotle's error was thinking of the terrestrial as being entirely different from the celestial. And it took a long time in the West before Isaac Newton made a physical system that combined them both. And it was fantastic to see that this is not an error in the Chinese view of things. The other thing that struck me as very interesting, of course, was this substantial error in the prediction of Mars that keeps recurring. A long time after I discovered this effect, I kept trying to figure out how to change the parameters in order to make it go away. And every time I made it go away, it simply popped up at a different date. And finally I realized that you couldn't make it go away by changing the parameters. You had to change the fundamental model. Now, my question is, you clearly have been able to plot those errors by using the system, but did anybody notice those big errors at that time?
Notice sometimes, yeah, as the emperor noticed, for example, he watched the sky, it's different, very different from what the prediction was. So, but not systematically noticed, yeah. So Senko tried to improve the situation, but his project just simply end up in abortion, end up without being carried out. Yeah.
So, to the extent that it was seen, nothing happened.
Nothing happened, yeah.
All right, I open the floor to questions for Professor Sun. Go ahead.
On one of your slides about Mars, there was a footnote that had some huge number for the number of individual calculations.
Yes.
And I'm just curious, who was doing those and how?
Oh. For example, for the first calendar from the Han Dynasty, they already use large numbers. Yeah, as you can see, I just showed you. Or,
yeah.
Yeah, here, maybe a little bit later. Yeah. So,
calculation has, I can't even read that number.
yeah, these are the, you see, number of days. Huh? No. Oh yeah, this one. Duration, days and parts, you can see. So these are the days and these are the parts. Then what is the meaning of the parts? For calculation about the mass, the day or 1 degree, the Chinese call it du, because the Chinese divided the sky into 365 and a quarter degrees. So that's different from 300. So these two has these parts. And for Jupiter, it has another number. So for each planet, it has a different parts. So this involves calculation of very large numbers, and they use it by sticks, by these calculating sticks. What's the? Yeah. These people are very good at this calculation. The description of how these people make calculations, I said they're moving these sticks so quickly you cannot even, it's like magic, and then they can produce these numbers. So some people nowadays, even without anything, they can do very large calculations. So if people are trained on this, they can do this kind of big number multiplications or subtraction, addition, or division. Yeah.
Charles.
So we hear a lot of in the popular press here about the Silk Road and the communications to the Middle East and
Yes.
the Arabian Crescent. Was there much exchange of astronomical ideas and information associated with that trade route?
Yes. Before 17th or 18th century, we do not know much, but still we see some similarities between Chinese and probably even Greek. One thing I would point out is about those astrological texts. That look so similar to the what is in the Chaldeans. Those the way, the format is so similar, but we do not have no evidence, no clue how this knowledge is. But after the Tang Dynasty, we mentioned this great expansion calendar of the 702-8, and China was already influenced by the Buddhism, from India. So actually, this monk, he had used some knowledge from India to improve his calendar system. After 13th century, then because of this Mongol, conquest, the exchange between Islamic world and China becomes very frequently. We know about, there's one person, Jamaluddin, he brought 7 instruments to China. And Guo Shoujing, this building of large instrument, we don't know whether he was influenced by the Middle East, the Arabic. Also, they also build a large instrument. That's a trend, in this old way. That's the only way to improve the accuracy of the observation. So I think there was, and of course at the end of the Ming we have these Jesuits come. So exchange in history, I think quite a lot. But before the end of the Ming, we do not do much study on this.
Yeah, you first and then.
Okay, thanks. I'm just curious, was there much discussion of cosmology, cosmological issues in the calendrical texts, so the calendrical systems, or do those texts deal with mathematical prediction, but not issues such as the shape of the Earth, shape of the cosmos?
That's a good question, yeah. In China, we have some cosmological speculations, like the hovering sky, we treat the sky and the Earth as parallel planes, and also the celestial globe. But somehow it has no connection with the actual numerical calculation of the calendar making. So that there is a kind of this, divide between the cosmological thinking but as in a calendrical text, the astronomers also they talk about the cosmological issues. That's the one often used is the numerology. So that means that all these numbers, for example, 19, that's for the period of intercalary months. They would say they use book of change. They say, well, this number is 10 plus 9, and the 10 is the largest, the Earth number, and 9 is the largest heaven number, the odd number. This plus together have this 19. In this way, they have give authority, kind of to these numbers, which probably they are acquired from actual observation, but somehow they want to mystify it. So that's the way often used by, for example, by this first calendar from the Han Dynasty. So that's where, in this way, they think numbers are real. Yeah. So the numbers really reflect what the universe is. So that's a kind of a belief deeply, I think, influenced their way of their rhetoric, their discourse, I think.
From above.
Yeah.
Yeah, so you talked about the 283 traditional constellations set up as early as 200-something AD, right?
Mm-hmm.
And so were those traditional constellations, in fact, very standard in the sense that when the Jesuits arrived in the 1500s, they would have seen, people would have been using the same constellations, or did it change a lot over that period? And a follow-up is, do people still use the traditional constellations in popular culture?
Last question, yeah. No more. Nowadays, people using these 88, constellation. The young people know more about the Greek constellation than the Chinese constellation. Yes, in the history, the Chinese 283 was fixed around the 3rd century AD by a person. He just conflated, put together various schools, which was probably from the Han Dynasty. So I did a study about the Chinese sky during the Han. That's a study of the Chinese constellations. And this system, these names, did not change ever. Later on, do no change. But the problem is what these names actually mean. For example, there was one star called the Southern Gate. It's in the Centaurus. 2,000 years ago, this star very high. It looks like two pillars, This looked like a Southern Gate. But now, when 1,500 years later, those stars no more visible. Then those Southern Gate is still there. Then people have to find another stars to name it as this Southern Gate. So, and also at the end of the Ming, when the Jesuits come, they also introduced those southern constellation, which was named by the Dutch, Houtman, and these 12 new constellations, and the Chinese, just separated it into 23 Chinese constellations. So at the end of the Ming Dynasty, the Chinese constellation included 283 and these 23 new southern constellations.
I have one more question. First, thank you for such a fascinating talk, Professor Sun.
Thank you.
At the beginning of your talk, you quote a sentence from the Book of Change, 易经.
Yeah.
天垂象，圣人则之.
Yes.
Is that right?
Yes.
Okay. So some people speculate that the Book of Change has something to do with 河图洛书, and some people associate 河图洛书 to the origin of Chinese astronomy. Do you have any comment on this? Or have you ever done research into 河图洛书?
Not much. Yeah. Now that's when you have a system of knowledge. People always want to trace its roots back to remote ancient times. That's a way, to give authority, authenticity to this. That's the Chinese like this. I think the Western people also like this. Like in biblical studies, they always want to trace something to the very remote ancient time. So I think, of course, it's related, but that's the way, the Han astronomers want to make their system looks good, looks authoritative. So that connected to this 易经 and also to maybe 河图 and 洛书, this. So that's my way of taking it. I didn't do much study on this, but it could be very interesting. Even so, it's very interesting to see how to make people believe what they did is true. That's important. Even for nowadays, for scientists, it's important, Do
you think that 河图洛书has something to do with some sort of
constellations or some sort of astronomical phenomenon, or
I have no idea. I don't think I didn't study on this, but I don't think these are just a range of numbers like a magic square. You know, it's not really related to constellations. But in some, recent excavation in the archaeological site, they do have discovered a total back the shell. Only there is these dots. Maybe people think these probably are those He-Tu rocks you are mentioning. And I examined it. It looks like a sundial. Yeah, if you put a stick in the middle, you see those dots indicate where the sunrise, where the sunset. So maybe in that way, that's my guess. But I haven't really studied on this. Yeah.
okay,
Thank you. Yeah.
Well, I'm going to ask you to thank Professor Sun again, but I want you also to maybe, when you see Ping Xiao around, thank him for suggesting this particular colloquium and having a big hand in getting it organized.